We're told that for this solid post, it has a diameter of 100 millimeters. And the stresses at A and B are what we're looking for. All right, so as we did in the previous problems, we want to start with our free body diagram cutting at the plane where, in this case, both A and B lie. So in this diagram, we can simplify this distributed wind load that's uniform. They give us the pressure of the wind, 1.5 kilopascals. In this picture, since we're going to be looking at what the internal loads are at that cut, we can simplify the distributed load down to a point load for this analysis without changing it. So that wind pressure that's going to be on there, I can simplify to a point load acting at the centroid, since it's a uniform load, acting at the by one rectangle. So the force due to that pressure will be the pressure times the area it's acting on. So 1.5 kilopascals times 2 square meters will be 3,000 newtons, since a pascal is a newton per meter squared. And it's acting at the centroid, so 1 meter from the left edge and 0.5 meters from the bottom edge. I'm going to locate my coordinate system at my cut surface, like I have previously. So where I'm cutting, I have to go out from that cut surface, so that I'm going to start with my internal normal force and my internal torsion here. So outward from the surface of the cut will be that normal force P, and positive around that arrow I just drew, that internal torsion T. I'm going to follow my coordinate system to draw. Now in the plane of the cut, I'm going to have my components of the shear, internal shear force. I'll have a Y component I'll call Vy. In X components I'll call Vx. I'll assume they're both in the positive directions, X and Y. And then around the Y-axis, My, and around the X-axis, Mx. So again, I'll reiterate, the force P always comes out from the surface of the cut. T we're going to assume is positive around that force P. And then since our coordinate system will, in these cases, always be in line with our surface of the cut, we can split our shear force into two components along the positive axes, and our bending moments around the positive coordinates, again, assuming positive directions for both. Questions about the free body diagram we have for this one? We can solve for our 6 internal loads at that cut surface here. In the x direction, we have Vx minus the 3,000 newtons from the distributed load from that wind force. So Vx is 3,000 newtons in the positive direction. In the y direction, we have Vy, and that's all that's in the y direction. And in the z direction, we have negative P, and that's the only force in the z direction. forces drop. And if I take the sum of moments around my cut surface, or really the centroid of my cut surface, I'm going to have here MXI plus MYJ minus TK for the three internal moments. And then I'll have one moment caused by that 3,000 Newton force using R cross F. So I need the distance from what I'm calling point Q to where that load is being applied. I have to go in the Z direction, 3.5 meters. And then in the J direction, I have to go 1 meter to get to that point. And the force is in the negative X direction. So that last row, negative 3,000 newtons. So this will be in Newton meters, meaning that MX, MY, and T will also be in Newton meters. Expanding that out, I would get MX equals 0, so the I component of this is going to be 0, and that makes sense because we'll have 1 times 0 minus 3.5 times 0. The J component will give me that My is 10.5 times 10 to the third Newton meters. I'm going to keep everything in base units right now. And the torsion T comes out also negative 3,000 Newton meters. All right, so we use these. We have to redraw. I'll draw the picture and then come back over here. I want to draw the surface of my cut. Again, looking straight onto it here. So I'm going to take this, since I cut it below this part, I want to look up, standing on the negative Z axis and looking up at the surface of that cut to do the rest of this. Right, so again, from this viewpoint, I'm standing on the negative Z axis looking at the surface of the cut. I'm going to rotate it up this way, meaning that the way I'm looking at it, Y is going to be to the right, and X is going to be up. And then Z will be into the board. And from this view, I want to map where A and B are. So again, originally A was at our front, but we're flipping this up, so now A will be located at the top. And B was on kind of the left in that picture, but we're going to flip it up, and B will be located over here on the left side. Again, I'm interested in, just to illustrate here, we're going to have a stress cube located at A, and a stress cube located at B. And what I'm trying to find are what are all the stresses acting on that tiny element of material located at A and located at B, due to these different loads that are acting on it. So what I can do is I can take the forces and moments that I have from the internal load solution and map them onto this picture. So I'll be able to use those more easily to find my stresses. So first, Vx was not 0, it was 3,000 newtons. In my original picture, I said it was along the X direction. It's positive, which means that that assumption was correct. So I will have a shear force of 3,000 newtons pointed in the positive X direction. Vy was 0, so I don't need it in this picture. P was 0, I don't need it in this picture. Mx is 0, I don't need it. My is not 0. In my first picture, I assumed it was around the positive y-axis. It was positive, so that assumption was correct. So around the positive y-axis, I'm going to have a moment. Wrong direction there. Around the positive y-axis here, I'll have a moment of 10.5 times 10 to the third Newton meters. And my torsion T, 3,000 Newton meters. In my picture, I said it was around the negative z-axis, which means since it was positive, that was correct. So around the negative z-axis, which is coming at us, I'm going to have my torque of 3,000 Newton meters. So yeah, the sign convention I use is going to follow what I said here. Whatever my assumptions were in my first free body diagram, I'm using that same coordinate system, but just from a different viewpoint. So I have to make sure that all the directions here are correct. So this is around the negative z, this is around the positive y-axis, this is in the positive x direction. Questions about the second free body diagram? So I have to consider what's happening at point A, what's happening at point B. So I want to look at the stress cubes that are going to be caused at each of those points. I'll keep track of that over here. So stresses that act on A, or both A and B, and stresses that just act on B. I'm going to consider all the cases separately and then superimpose them together to get my final answer. So I'm going to have potentially three stresses here, one caused by the torsion, one by the bending moment, and one by the shear force in the x direction that could affect my cubes in this case. So I like to start with the easier ones. If we have like P over A, in this case we don't have P, so there's not going to be an axial stress. The bending moment is usually another easier one to do. We will have a bending moment caused by the moment around point Y. A will be affected. Will B be affected? Right. B is not because, again, from the perspective of this moment, it lies on that neutral axis. So in this case, A will be maximally affected because it's the furthest away. It's at the top relative to this horizontal neutral axis. B will not be affected. So the stress going to be caused at A, will this bending be tensile or compressive on point A? It'll be tensile because at the top, it's going to be pulling this material out, and below the neutral axis, this moment will be pushing the material in. So we know at point A, this will be a tensile force. And remember, in beam bending, we want to use the negative my over I. Here we want to know from our picture already, is it tensile or compressive? And then use all positive quantities for m and y. So my over I, but we know it's going to be tensile. Actually, we can calculate right now the value of I because it's a solid circular cross-section. Will be pi over 4 r to the fourth. So our value of I, we get 4.91 times 10 to the negative 6 meters to the fourth power. And since we're going to need it in a bit anyway, I'll get J, which will be twice I for a circular cross-section. 9.8 times 10 to the negative 6 meters to the fourth. And also helpful here would be cross-sectional area if we had an axial stress. In this case, we don't. So the A won't be particularly useful, but we can do all of this before we even look at stresses, since I is used in multiple calculations. All right, so the bending stress at A, we're going to use the moment around the neutral axis, so 10.5 times 10 to the third Newton meters, times the distance between A and the neutral axis, which will just be the radius, 50 millimeters. Divide by that cross-sectional area, 4.91, divide by the moment of area, 4.91 times 10 to the negative 6 Again, we know it's tensile, and it's going to have a value of 107 megapascals. As we said before, this stress affects only A, and we know it's tensile because we're above the neutral axis. It's going to be tension in tension. Below the neutral axis would be compression. So the first stress acting on A is this tensile stress of 107 megapascals. And these blocks will be oriented in the same direction as this surface. So it's acting on that Z, on the negative and positive Z faces, a tensile stress of 107 megapascals. And we said B will not be affected by this because it lies on that neutral axis. Questions on the bending stress caused by the moment around the y-axis. We have the torsion, the 3,000 Newton meters, will cause a shear stress on these faces. Which of these points will be affected by the torsion? We'll have a stress induced because of the torsion. Right. Both A and B will be affected by this. By the torsion would be one at the center. Distance from the center, its rho value would be 0. So the magnitude of the stress caused by this 3,000 Newton meters will be the same on A and B, although we'll see that the direction is different. But because they both have that same value of rho, the T rho over J will have the same value. So we know that our internal torsion was 3,000 Newton meters. Both A and B have the same value of rho, which is just the radius in this case, 50 millimeters. And the J we calculated before, 9.8 times 10 to the negative 6. Shear stress caused by the torsion, 15.3 megapascals. So both A and B are affected, so both of them will have to add this effect to their stress cubes. Right, so the front face, the negative Z face, we know that when we get around here, the torsion will be pushing to the left. It's tangent to the circle. So on the front face, we're going to have a leftward pointing shear stress. And the shear stresses are going to be matched. So we would also have one on this positive Y face that's pointing in the positive Z direction. And we can't see it in the picture, but we would have on the back face, we would be pointing to the right. On the left face, we would be pointing forward. But yeah, we get all that information if we know one face. We know what's happening on the others. The arrows have to match each other or point to each other in the corners. They have to be equal and opposite so that the net effect is 0. And that is going to be 15.3 megapascals. Going to be down as we follow this through. It's down on that front face, which means to balance it out. On the top face, it's going to be pointing back. On the bottom, forward. And on the back face, it would be pointing up. But the magnitude is the same, 15.3 megapascals. Right, so lastly, we have to take care of that shear force in the x direction. That's taken care of. So that 3,000 Newton force is going to cause a transverse shear stress. Again, we have to consider what's the stress going to be at A, what's it going to be at B. So first is, are either of them going to be 0? So we don't have to do a calculation for those. Right, A will be 0 because for transverse, it's going to be 0 at the top and the bottom of the cross section. So with respect to, again, that horizontal neutral axis here, A is at the top. So the Q value will be 0 for point A. So there's no shear stress from the 3,000 newtons that's going to be at A, but at B, because it's on that neutral axis, it will actually be at its maximum value. So we only have to calculate the transverse shear stress at point B, since A will be 0. We know that the force is 3,000 newtons. We know the value of I. So if we're interested in the stress at point B, we have to make a cut across the cross-section on the plane that point B lies on, or the axis that point B lies on. In this case, that is also the neutral axis. So we're cutting everything either above or below that, but it's symmetric in this case because we're cutting at that neutral axis. What is the length of material that we're cutting through to make this mini shape? Right. We're cutting through the diameter, which we said was 100 millimeters, or 0.1 meter. So it's not the radius, it's the diameter. It's all the material we cut through to make this mini shape. And the value for Q in this case is going to be the area of our mini shape times the distance between the centroid of the mini shape and the neutral axis. So the area is just going to be 1/2 pi r squared. And the distance between the centroid and the neutral axis for our mini shape, for the half circle, we use 4r over 3 pi. We don't need to make a whole table for this one because it's not a composite shape, it's just a half circle. So it's area times the distance between its centroid and the neutral axis. So putting this all together, we get that the shear stress caused by that shear force is going to be 509 kilopascals. And this affects B, but it does not affect A. Right, so if we look at the stress cube at B from this, what's it going to look like? What kind of stress are we going to see? Right, on the front face, it's going to be in the same direction as that 3,000 newtons. So it's up on the front face, forward on the top, back on the bottom, and down on the back. But really the ones we see, it's going to be up, and then we see these are going to be in opposite directions. This is 509 kilopascals. So putting it all together now, I can draw my total state of stress, and I'll redraw my coordinate system here that I'm aligned with. And the shear stress is 15.3. So that's my complete state of stress for point A. At B, I have no normal stresses acting at B in this scenario, but I do have two shear stresses. They're in opposite directions. So because they're in opposite directions, I have to take their difference. So I need 15.3 megapascals minus the 509 kilopascals to get the total stress. So pointing down, I'm going to have 14.8 megapascals of shear stress.